Welcome! This is the third of my videos in the series about understanding space weather. This one's going to deal with what goes on inside the sun. As I mentioned before, I'm writing a series of 5 papers on understanding space weather for the American Meteorological Society. It will appear in their journal, the Bulletins of the American Meteorological Society. One has already been published. The second and third will be available in the November and December editions respectively. A couple of them are already available online and you can check them out in the URLs listed below. As we learned in earlier videos, the sun is a star. Many years ago, an extraordinarily talented Indian mathematician called Chandrasekhar derived an equation for stellar structure. He balanced the forces between gravity, which was trying to crush the star into a small volume, and the outward pressure of the hot gases in the core of that star. And he came up with an equation that determined that we had a hot, dense core and that the density fell off exponentially as a function of the percentage of the radius of the star. It works for all conventional stars. It even works for globular clusters. Stellar theory for a star like the sun indicates there should be 3 different layers inside the star. The first is the core region, which we learned about earlier, is where the energy is generated, and that takes up about 10% of the radius of the star. Above that is what's called the radiative zone, which stretches from about 0.1 of the radius to 0.7 of the radius of the star, and that is the volume where radiation, i.e. photons, are the primary method of transporting energy out from the core of the sun. The third layer is the convective layer, which stretches from about 70% of the radius of the star to the surface. And here convection is the primary method of transport of energy to the surface of the star. We learned about the core in an earlier video, and we found out that the sun was producing about 4 times 10 to the 26 joules per second. That is produced by nuclear fusion in the core. That is the transformation of hydrogen nuclei, protons, into helium nuclei. And in that process, the sun produces a large number of gamma rays, some positrons and some neutrinos. The positrons can further be annihilated with an electron, forming yet more gamma rays. So in the core we have this flux of gamma rays trapped, and the only way they can move is outwards towards the surface of the sun. But they don't reach the surface of the sun as gamma rays. Every time they're absorbed and re-emitted, they're re-emitted by a slightly cooler plasma, so the wavelength of the photon is increased, so it's a lower energy photon. So by the time it gets to the surface of the sun, it's an optical photon, the sort of photons that we can see. The interesting thing about the energetic core of the sun is that the energy density there is relatively low. If you took a cubic meter at the core of the sun, the amount of energy being produced by it is about that equivalent to a 30-watt light bulb. So how come you get so much energy from the sun? Well, the sun is very big. Over 1 million Earths would fit inside it. The core being 10% of the radius of the sun means that there would be about 1,000 Earths that would fit inside the core. So we've got a large volume producing a small amount of energy, which sums to a large amount of energy. When I'm giving talks about the sun and tell people that the sun is losing 4 million tons of material every second, I keep getting asked the question, well, will the sun run out of mass? Well, let's do a quick calculation. There are about 32 million seconds in a year. We claim that the remaining life of the sun is about 4.5 billion years. So the total mass loss over that time would be 600 trillion kilograms. Now let's compare that with the total mass of the sun. That's 2 times 10 to the 30 kilograms. So the mass loss represents only 0.03% of the mass of the sun. So the sun is only going to lose a tiny fraction of its overall mass between now and the end of its useful life. So that's not one concern that should worry us. The layer immediately above the core is called the radiative zone, and that is because radiation, i.e. photons, is the primary source of energy transport in this zone. So this stretches from 10% of the solar radius to 70% of the solar radius, and the radius of the sun is nearly 700,000 kilometers, and the light travel time for that radius is between 2 and 3 seconds. However, as we've learned before, The actual travel time is more like 30 million years. That's because the sun is so dense. Photons that are trying to escape from the sun get bounced around in what's called a random walk process. Say the photon starts here at 0, 0. It's going to move a certain distance before it hits a nucleus and is absorbed, and then is sent out in a random direction. It can go forwards, backwards, or sideways. So this photon is going to get bounced around all over the place, and the denser the material, the more often it gets bounced around. And this is a calculation of a random walk, as it's called, where a photon tries to escape from a very dense medium, and eventually it ends up here after a certain time. And so the actual time to get from here to there is the distance traveled in order for it to escape. And in the sun, that is 30 million light years. The topmost layer of the solar interior is called the convective zone. Is where convection is the primary method of energy transport. At the base of the convection zone, the temperature is 2 million degrees Kelvin. At the surface of the sun, the photosphere, it's about 5,700 degrees Kelvin. So this sets up hot plumes of plasma rising to the surface, cooling, becoming more dense and falling back, only to be reheated. That's what basically convection is. You can actually see some of the convection cells if you look at the solar granulation. Each one of these features on here is the top of a convection cell. Until now, this has been mainly theory. We have a few observations to back that theory up. We see the neutrinos coming from the sun, we see the amount of energy coming from the sun, and at the surface we can see those convection cells. But is there a way of confirming the model, actually looking inside the sun? And there's a new branch of solar physics that's come up in the last few decades called helioseismology. The sun is buffered by a large number of sound waves at different frequencies. Some of those frequencies actually resonate with the structure of the sun. So you can build up a sonogram of the sun by observing the modes of oscillation of the sun. And that basically confirms the structure that we've been talking about. It confirms Chandra's original model. Well, with this tremendously powerful new tool called helioseismology, what can we learn? Well, we've already learned that the density structure predicted by Chandrasekhar is correct. But what else can we learn? One thing, we can determine the velocity structure inside the sun. We already knew from surface measurements that the equator rotates faster than the poles, about 27 days at the equator, 34 days at the poles. But with helioseismology we can look inside the sun and see how that rotational structure changes, and that's very important, as we'll find out in future videos about how sunspots are formed and how the solar cycle works. One remarkable thing that you can do is actually see sunspots on the far side of the sun, the side of the sun that's facing away from the Earth. These sound waves that helioseismology is monitoring get interfered with by sunspots. So you look at a sound wave that travels around the back of the sun. If it's interfered with at certain longitudes and latitudes, then you know that there's a sunspot there, and you can build an image up of the sun on the far side without actually having to see it directly. And you can actually look beneath sunspots by looking at the local variations around a sunspot. You can actually see what's going on beneath the sunspot, which again is something that we've never been able to do. In the next video, I'm going to talk about the rotating sun, or to paraphrase Rudyard Kipling, how the sun got its spots. In fact, many people don't know that the sun rotates. I'm going to describe how the sun rotates, how that might generate magnetic fields, and exactly what are sunspots. So until next time, stay safe.